Okay, we're going to continue with our treatment of Chapter 9, and we're starting with vapor pressure, of course, here. And I just want to quickly review what we talked about today. Basic differences between solids, liquids, and gases, and the basic idea of vapor pressure, starting with a dry headspace above water or liquid, any type of liquid really. And then what we get first is we get some evaporation that starts to add molecules, gaseous molecules, to the headspace, and these molecules are bouncing around up here. And as the concentration of these molecules increases, then we get condensation. We start to get condensation. And we could put that on a graph of rate versus time, and we'd see that the evaporation rate right here is a constant because it's a function only of the temperature of the liquid. And then the condensation, however, increases over time because it is a function of the concentration. So the rate of condensation is a function of the concentration. And then if we actually plot the concentration of H2O gas, by the way, concentration is not a way we typically look at gases, but we can if we want, and moles per liter of volume. So if we look at that over time in this same system, here's what we would see. We would see that the concentration of water would reach a constant value. Now, as I mentioned, once we reach that constant value, at that point, the vapor pressure becomes a constant. The pressure exerted. So, and this we'll say also that we are at equilibrium. So equilibrium occurs when the rate of condensation equals the rate of evaporation. Now, what this means, though, or one consequence of this, let me redraw this graph here, is that if we increase the temperature, then we'll see something like this. Let me get a different pen. If we increase the temperature, then the only thing that will change is that this point here will go up. And then if we were to raise it up even higher, so we're to increase the temp even more, we'll see something even higher up here like this. So this would be increasing temperature. So, and we can view that in a graph here. Oops. This is a graph showing the, let's see, I'd better move this down. The vapor pressure of 4 different liquids. We've got temperature on the x-axis, and we've got the pressure being exerted by the vapor on the y-axis. And let's just focus in on water here for a second. We notice a couple things. First of all, we see that the vapor pressure is increasing as we increase the temperature of the system, as I just showed you. And the other thing we'll notice is that 101.3 kPa, at that pressure corresponds to 100 degrees C. Now that happens to be 100 degrees C is the boiling point of water, and there's some significance to this, which we will talk about soon. But another thing I want you to notice is that the vapor pressure of the substance at a given temperature depends on what substance it is. Look at ethanol; it exerts a greater vapor pressure at a given temperature. Now let's go back here and look at our drawing, at our what we were saying here. Let's take an example. So one of the most common types of problems that you'll have with this is to say something like this. Well, let's start with the simplest case. So what is the pressure exerted by the H2O gas? And you've seen this sort of thing in some of your labs before. Above liquid H2O at, let's say, 50 degrees C. So in a real simple question like this, we would just look at our graph. We'd go to 50 degrees C, we'd trace it up here to the water line, trace it across, and it's looking like maybe about 12 kPa. So the answer is 12 kPa. Now 101.3 kPa is 1 atmosphere. All right, so it's not very much, and you've noticed this when it's in millimeters of mercury, it's low as well. Now, does this mean that's the total pressure in this headspace? No. For example, if we had started with an open container and then we shut it and then we let the water come to equilibrium, then the pressure total is going to be equal to 101.3 kPa, which was, let's say that was the atmospheric pressure at the time, plus the 12 kPa. All right, and you've done this sort of thing in labs. Now let's get a little bit more complicated. Let's say we state the question a little bit differently. We start off with a dry container, and we put, let's say, we put in here, we're going to place 0.01 moles of liquid benzene. And this is a 1 liter container, and it's at 25 degrees C. And then we're going to seal the container. And the question is, how much, so let's say this is our 0.0100 mole of liquid benzene, how much benzene evaporates? Now, we don't know that it's going to be all of it, right? I mean, it might be all of it that evaporates. But if 0.0100 mole of liquid benzene would not fill the 1 liter as a gas, then at the vapor pressure of benzene at 25 degrees C, then it will all evaporate. But if we could fill this volume at the equilibrium vapor pressure of benzene at 25 C, then not all of it will evaporate. That was kind of confusing. So let's do the calculation. First of all, we need to know that at 25 degrees C, so you'd have to be given this piece of information here, the vapor pressure of benzene is 92 millimeters of mercury. Notice that that's quite a bit higher than the value we were looking at for water. So here's how we're going to approach this. We're going to say, okay, how many moles of vapor would fill that flask at 92 millimeters of mercury pressure? So number of moles of vapor. And by the way, a vapor is just a gas. We tend to use the word vapor when we're dealing with something that we normally encounter as a liquid, and it happens to be a gas at this point. So we'll typically use the vapor term then. So PV over RT. And now what we've got is 92 over 760. That's going to give us the pressure of the vapor in ATM. The volume is 1 liter, 0.0821 liters atmospheres per Kelvin mole, and the temperature is 298 K. So this comes out to 0.0050 mole. That is the number of moles of benzene that would fill this flask at 25 degrees C and 92 millimeters of mercury, which is the pressure exerted by the vapor. It's equilibrium pressure. Now here's the deal. The number of moles, this is the number, well, this is actually the answer to how many moles evaporate. But one thing we want to check is say that 0.0050 moles is obviously less than 0.0100 moles, which is the liquid that we had at the beginning. So the answer is that 0.0050 moles evaporates, leaving 0.0050 moles liquid. Now, by the way, if you let this sit long enough, what would happen is it wouldn't always be the same 0.005 moles of liquid, because there's a constant exchange between the liquid and the gaseous state. And we could also go further and say, if the flask were made larger, it would all evaporate. And we could actually calculate, we're not going to take the time right now, but we could obviously make the flask large enough that it would all evaporate. If we make it much larger, and the pressure of the benzene would be less than the equilibrium vapor pressure, 92 millimeters. So we could keep making it larger, and then the benzene would be obviously exerting less pressure, and we could take that into, we could figure out how much that pressure is using the ideal gas law. Now, we looked at this graph a minute ago, and you might wonder if there is an equation for this graph, and that's true, there is. So we want to look at the temperature dependence of vapor pressure. And we're going to use something called the Clausius Clapeyron equation. And the form that we're going to use most commonly looks like this. And of course, what I should change this. Sorry, just write delta H vap. Delta H vap is the heat of vaporization. However, it's in joules per mole. Not kilojoules like normally, so we're just going to have to convert it to joules. And then R is the gas constant, but in this case it's 8.31 because we're changing it to joules per mole Kelvin. And given any two temperatures, well, given a pressure and two temperatures, we can calculate the second pressure and so on. Now notice here that these two correspond to each other, so this is a vapor pressure and a temperature pair, and then the P2 and the T2 are a vapor pressure and temperature pair. It'll make more sense if we do a problem, so let's try that out. Here's a problem. Take the heat of vaporization of benzene to be 30.8 kilojoules per mole. And we know from above that the vapor pressure at 25 degrees C of benzene is 92 millimeters of mercury. Okay? Then we can ask, what is the vapor pressure at 50 degrees C? So isn't this interesting? We've got, we know the vapor pressure at one temperature, and we know the heat of vaporization, and we can then calculate the vapor pressure at any other temperature. So let's try that out. We've got ln P2 over P1. Oops, by the way, what is this? This is the natural logarithm, right? It's a log-based E, where E is the natural number. And we'll take a look at how to do these calculations as we go through this. So we're going to have 30,800 joules over 8.31 joules per mole Kelvin. You'll see the joules will cancel. And then 1 over 298 minus 1 over 323. So I'm taking this to be my T1, right? 298, and this is going to be my T2. Now you'll notice that we could have filled in P1 here with 92 millimeters of mercury, but we're going to wait on that because watch how we're going to solve this. First of all, this side of the equation is equal to 0.963. Now that means that the natural log of P2 over P1 is equal to 0.963. Now how do we get, what we want to do is we want to get at this ratio, right? So we've got to extract that from the natural log. So the way we're going to do that is we raise both sides of the equation, we raise E to both sides of the equation, to the power of both sides of the equation. So on our calculator, we're going to simply type in on my TI-83 Plus, I'm going to click second ln, which is e to the x, and I'm going to type in 0.963, and I get 2.6195. So what happens is e to the 0.963 is 2.6195, and e to the ln p2 over p1 is simply p2 over p1. And you might want to check the appendix in the textbook about doing calculations with logarithms if you're unsure of what's going on here. And now I can just solve for p2 because I know what p1 is. So I've got p2 is equal to 2.6195 times p1, which is 92 millimeters of mercury. And notice I don't need to do a conversion here with the millimeters of mercury. In this case, 241 millimeters of mercury. Wow, that's pretty high. Look at that. We're at what temperature? 50 degrees C, and we're almost at atmospheric pressure with the vapor pressure. Much different situation than water. Note that the pressure more than doubles as temperature rises from 20 to 50. This is reflecting the fact that more benzene vaporizes. Notice that this is not an ideal gas law effect. So this increase is not a PV equals nRT effect. Okay? The effect of temperature on pressure, so the effect of temperature on pressure from this would be only around 10% increase. So if we were going to look at the increase in pressure due simply to the temperature increase, it would be only about 10%. Alright, let's talk about boiling point. I already hinted at this when we were looking at this graph, and I mentioned that at 100 degrees C, which is the boiling point of water, it just so happens that the vapor pressure, the equilibrium vapor pressure, is 101.3 kPa, which is equal to 1 atmosphere. Now, why is that? If you think about a boiling beaker of water, in order for water to boil, basically what boiling is boiling is evaporation throughout the liquid volume. As we mentioned that evaporation is constantly happening at the surface, right, at various rates depending on the temperature. But if it is happening throughout the volume of the liquid, then that's boiling. So in other words, we've got bubbles of gas. Now, when you see those bubbles forming when water's boiling, what's happening? Those are bubbles of H2O gas. It's gaseous H2O in those bubbles. So when they're forming all over here, think about this. If you were, let's say you were an incipient bubble, so you are a bubble wannabe. You are the thought of a bubble. In order to form a bubble of gas, so you're going to say to a bunch of your water molecule friends, let's get together and form a bubble. Well, you've got to form a gas. What pressure would you have to exert? So in other words, in order to push out and expand a space for yourself, you would have to exert a pressure that was at least equal to the ambient pressure. And standard atmospheric pressure is 1 atm. Now it does fluctuate, and so you would expect the boiling point to fluctuate. But you've got to exert at least 1 atm. So basically, when you're on this curve and the vapor pressure is increasing, once you get to 100 degrees C, the pressure exerted by the vapor in equilibrium with its liquid is 1 atm, and that's when boiling occurs. Now, if you're up at the top of a mountain, so you're up at the top of a mountain and you're trying to cook your stew, right? What's going to happen is it's going to take longer to cook. So if you're trying to cook stew, you're boiling vegetables and meat in a pot. What's going to happen is it's going to be boiling at a lower temperature. So the boiling point on the mountain will be lower because the atmospheric pressure is lower. The atmospheric pressure is lower on the mountain because there's less atmosphere above you. You're closer to the, you're closer out of space essentially, so there's less air pushing down on you. And so what's going to happen is this is going to take longer to cook because it's not going to be boiling at 100. It might be boiling at 90 or 95 or something like that. So that is where boiling point becomes very much linked with this idea of vapor pressure. So let's look at an example here. The other application of this, is a pressure cooker. So I don't know if you've ever used a pressure cooker, but it's got a lid that locks onto the top of the pot, and it has a little valve up here that has a weight that holds it closed, but pressure can escape to a certain extent. So you heat this thing up on the stove, and the pressure starts to rise in here, and it gets up to, let's say about it gets up to 1075 millimeters of mercury. Well, what happens now, you're raising the pressure over here, so your boiling point is going to be higher. So the temperature at that point might be 110 degrees C. So you've gotten 10 degrees more, and what happens is you can cook faster. So sometimes these are called speed cookers. In contrast, if the pressure is equal to 5 millimeters of mercury, which is very low, then the temperature of boiling is going to be equal to 0 degrees C. So water will actually boil at 0 degrees C. Now we can kind of graph this all out on something called a phase diagram. In a phase diagram, you've got the temperature and the pressure, just like we had in the previous graph we looked at. But in this sort of diagram, we're going to show a broader range of temperatures and pressures. So we're going to get something like this. And what's going to happen is down here, you're going to have the gaseous state. Up here, you're going to have the liquid state. Over here, you're going to have the solid state. So, for example, let's say I had a cylinder, or let's say a syringe, because I'll show you a syringe tomorrow. And I'm going to put a cap on here, and there's a plunger. All right. And if I start with, say, H2O gas, well, what would happen if I compress that? So I'm going to change the pressure on that H2O gas. I could push it down enough. If, let's say, I start at a given temperature, maybe I'm at 25 degrees C here, and I start to increase the pressure, I could actually change it into a liquid. That's what this graph predicts. Now let's say I'm in a liquid state and I decrease the temperature. What'll happen? I can change it into a solid. Now if I'm in the solid state and I decrease the pressure low enough, I can actually change it into a gas. That would be called sublimation. Sublimation is going right from a solid into a gas. So this is kind of how phase diagrams work. And one thing you should know also is a couple of other points that are named on this. Right here, this is called the critical point. And basically right here, this is the highest temperature at which a liquid can exist. So we could even cut this off right here. Although what they say is that above this point, it's usually called a supercritical fluid. But that's the temperature above which liquid can no longer exist, regardless of the pressure. And this point right here is called the triple point. And that is the point where you can have a solid, liquid, and a gas all present at the same time. So that's a phase diagram. Now we want to focus in here on intermolecular forces for a bit, because it's the intermolecular forces that really kind of determine the shape, not the shape of this diagram, but but where the points are going to be in terms of what temperatures, where's the boiling point, where's the triple point, where's the critical point. It's going to be intermolecular forces. Those are the forces between molecules. Okay. By the way, this graph right here is actually for water. And the reason I say that is because you see the way this line is sloping? This is telling me that if I start with a solid and I increase the pressure enough, I can turn it into a liquid. That's actually true for water, and that's how ice skates work. So the ice skate concentrates the pressure on a small line on the ice, and what happens is the ice melts and creates like a thin layer of liquid under the skate, and it gives it a lot of reduces the friction. Most substances, though, would have the solidus line with a positive slope, so it would look like this. In other words, if you start with a liquid and pressurize it, it would change it into a solid. When you think about it, this kind of makes more sense because, and the reason it's usually like this is that in solids, the atoms are a bit closer together than in a liquid where they're all kind of sliding past each other. In water, the reason it works the reverse in water is because in water, the water molecules are arranged in kind of this open hexagonal network, crystal structure. So there's this fancy crystal structure where there's open space in between here when you're talking about ice. And so ice is actually less dense than liquid water. That's not true about most substances, though. Okay, sorry, that was a sidetrack. Intermolecular forces, these are simply, so when you think of think of international. These are forces between molecules. And we have two basic types of intermolecular forces, and those are dipole-to-dipole forces, or dipole-to-dipole interactions, and what we call dispersion forces. And within dipole-to-dipole interactions, we have an especially strong form called hydrogen bond. They're a special case, and very important case because they're important in water, liquid water. Now let's look in a little bit more detail at what's going on with these. Number one, dipole-to-dipole interactions. If we take a polar molecule, let's say HCl, so we've got one HCl molecule. Now if we've got more HCl molecules around, we know first of all that these are both polar, right? So this end of the HCl molecule will be negative, and this end will have a partial positive charge, partial negative, partial positive. So what would be the interaction between these two molecules? Well, obviously the positive side of this molecule right here would attract the negative side of this molecule just by, according to Coulomb's law. So this attraction is what we call the dipole-to-dipole interaction. By the way, a dipole is simply a polar molecule. And it is this sort of force that makes the liquid state possible. So these intermolecular forces, they make liquids and solids possible. And I'll mention that, I'll get back to that again later. So in a dipole-to-dipole interaction, you've got two polar molecules. So these are between polar molecules. It's simply the negative end of one molecule attracting the positive end of another molecule. Now, a very strong case of this is given a special name called hydrogen bonding. This is really a bad name because this is, even though it involves hydrogen, the word bonding makes it seem like it's a covalent bond. It's not. This occurs when you have a highly electronegative element like oxygen bonded to hydrogen in a molecule. And this creates a special case because oxygen is so electronegative that it hogs all the electrons in these bonds. And it pretty much leaves the hydrogens as like naked protons out here. So most of the time, those hydrogens are nothing but a naked proton sitting out there, and these electrons are being hogged by the oxygen. And it's because oxygen has such a high electronegativity, and because hydrogen only has one electron, it ends up as kind of a naked proton. Now, the consequence of that is if there's another oxygen over here, another water molecule, this proton can get right in, almost into the electron cloud of this oxygen. It can get very close because it's just a naked proton. There's almost no repulsion there because these electrons are usually pulled down toward the oxygen. So we get a very strong force of attraction called the hydrogen bond. Those dots right there. This right here is not the hydrogen bond. Okay, the hydrogen bond is between the molecules, and this is a very strong force of attraction. Very strong force of attraction. So, and this is why water has an exceptionally high boiling point for its mass. It's a very light molecule, and yet it has a pretty high boiling point for a molecular substance of its size. Why did I bring up mass? Well, let's talk about dispersion forces. Dispersion forces are a type of intermolecular attraction that occurs between any molecule, whether it be polar or nonpolar. So this occurs even between nonpolar molecules. And in fact, it's most important with nonpolar molecules because they don't have the other types of forces. So let's look at this. Let's say we have a hydrogen molecule, H2. It is possible to have liquid hydrogen. It's not terribly common, but in liquid hydrogen, what would be holding the hydrogen molecules to each other? There's no negative end and positive end, so it can't be that, or can it? Look at these two electrons in this bond. What are they really doing? They're actually, there's a couple different ways we could look at it. If we look at the electron as a particle, then they're just randomly moving around, right? So they're forming a cloud, as it were. Of course, that's just two electrons, right? And that's just their random position. Well, is it possible that at one point both of those electrons would be at one end of the molecule and none of them would be at the other end? Sure. If that would happen, at that instant in time, the molecule would become polar, maybe just for a picosecond. But that would be enough to make it stick to a neighboring molecule. Why? Because we would get, so what we would have first of all is called a temporary dipole. And then what would happen to the neighboring molecule, if there was another molecule around, is that this negative charge, these electrons, now would repel the electrons in the neighboring molecule and push them down to the end, creating induced polarity in this molecule and a force between them, between the negative end, the temporary negative end of one molecule and the temporary positive end of another. So, but this would be very transient. And if you imagine a container with liquid hydrogen in it, and pick any two given molecules, they might be attracting each other at one point but not at the next. So if this were liquid hydrogen, I might say, oh, here's an attraction. Oh, now it's over here, now it's over here, now it's over here, now it's over here, now it's over here. So it's moving all through the liquid. Now, if you're asking the question right now, well, what if we think about electrons not as a particle, but as a standing wave? Well, now I think we need to look at it as a collection. So if the electrons in this bond are just a standing wave, just a pattern of charge. Well, what happens if I put another molecule next to this? Isn't that going to change the shape? Sure it will. It will affect the shape of this wave. It'll affect the nature of it, and it'll change the electron distribution, which might change the electron distribution around this one, the charge distribution, sorry, which might change the charge distribution around this one, and so on, and we get the same effect. But it's easiest to think about dispersion forces by thinking about electrons as particles. It's generally a weaker force, but it can get stronger. The dispersion forces get stronger as the size of the atom or molecule increases. Dispersion forces increase with molar mass, the mass per mole. Why is that? You might be tempted to say, well, if a molecule is bigger, then it's going to have a harder time, say, getting up out of the liquid and lifting itself up because of gravity. That's not true. It's not about gravity. Let's look at an example for one thing. If we look at the boiling point changes of these molecules. The boiling point of fluorine is less than the boiling point of chlorine, which is lower than the boiling point of bromine, which is lower than the boiling point of iodine. Now, why is it? Why is that? Well, these are larger molecules, and actually they're made of larger atoms. The outer electrons are further from the nucleus, and less tightly held. I mean, there's going to be a correlation here with ionization energy, obviously. This right here is the same thing as saying decreasing ionization energy or decreasing electronegativity. So the electrons are more easily dispersed. They're more easily pushed around to various sides of the atom, and so we get a greater dispersion force. More easily dispersed. Now, there's something else that is a very interesting effect, though. When we look at the alkanes, for example, organic compounds, so larger organic molecules, we see like this. The boiling point of CH4 is less than the boiling point of C2H6, which is less than the boiling point of C3H8, which is less than the boiling point of C4H10, and so on. Now, why is this? In this case, and by the way, you can, if you take this to its extreme, you take things like motor oil, which might be a chain of 36 carbons, and motor oil might have a boiling point of 400 degrees C or something like that. I'm not sure exactly what it is, but like think a typical vegetable oil is around 400 degrees Fahrenheit. So you can get some really high boiling points with some really non-polar molecules. Why is that? And it's not because the atoms are so big and because the electrons are more easily pushed around. Here we have to look at a different effect, surface area. And the other thing, so there's a larger surface area that can interact here, and if we've got dispersion forces going on, we've got some dispersion of electrons, there's more contact area between the molecules. And this is actually, it's interesting that you see this effect in a case like this. Let's look at C4H10, for example. So C4H10 could be like this, where you've got the straight chain, or it could be like this, where you've got a carbon coming off here. And these, by the way, would be isomers. Now, which would have the higher boiling point? It turns out that it would look like that, because this guy is kind of more tightly pulled in together. It's got less surface area, so this would have the higher boiling point, and this would have the lower one. Now let's look at a little bit though at the relative importance of these forces in determining boiling point, for example. So we're going to look at which one is most important. On page 272 in your text, there's a nice table, and I'm just going to use that. I'm going to talk about this. Let's compare. Now let's look at a good comparison here. Bromine, which liquid bromine, which has a boiling point. Well, it's not liquid when it's boiled, but it has a molar mass of, well, let's put it like this, molar mass of 160 and has a boiling point of 59 degrees C. Let's compare that with iodine chloride. Iodine chloride has a mass of 162, so it's slightly larger, but not enough to account for this kind of difference in boiling point. Look at that jump right there. That's a big difference. Typically, if we're looking at a molar mass effect of 2, well, let's do a side issue. I mean a little side track. Page 271. Just to compare the effect of a small change in mass. Let's see if I've got one here. I don't have any good example. Those are all large changes in mass, so you'll just have to trust me on that. That's a big jump. That's mostly due to the polarity. How about the effect of hydrogen bonding? Here we see some really dramatic effects. So H2O versus H2S, for example. H2O has hydrogen bonding, and it has a boiling point of 100 degrees C. And H2S does not have hydrogen bonding, although it's polar, and it's negative 60 degrees C. Hydrogen bonding has a huge effect that overwhelms the effect of the increased size of the sulfur atom. Now, like I mentioned, there are lots of oils that might boil at over 400 degrees C. So don't get it in your head that water has like the highest boiling point of anything. I mean, obviously iron boils at a much higher temperature as well. So it's not that this has the highest boiling point of everything. It's just for its size, it's got a very high boiling point. And that reminds me that I forgot something. So let's scroll up to where we were talking about hydrogen bonding. And we forgot something here. It's not just oxygen that can cause hydrogen bonding, but any compound that has nitrogen, oxygen, or fluorine bonded to H in the compound can contribute to or can participate in hydrogen bonding. So, for example, we can also look at ammonia, which has hydrogen bonding because it has a nitrogen bonded to hydrogen, so it can do hydrogen bonding with other similar molecules. The boiling point of ammonia is negative 33 degrees C, whereas the boiling point of phosphine, pH3, is negative 88. So again, this is a hydrogen bonding effect. We get a big jump in the boiling point when we have hydrogen bonding. Okay, and I think that's where we'll stop for now. So hopefully you get a chance to check this out before class tomorrow, and we'll wrap up chapter 9 tomorrow.